I wanted to give you a little commercial for the CS282 class that we'll be doing in the fall. A couple of very perceptive people noticed that the course catalog says that CS282 is only taught in the spring. I'm not quite sure where that's left over from, but we're breaking the rules and doing it in the fall. So that course is going to be focusing on mobile software development with Android and patterns and frameworks and good stuff like that. And if you go to my YouTube channel, which you should hopefully know at this point because that's where you get the 251 stuff. Here's the 251 playlist. There's also something that's now called the POSA MOOC 2014 channel, and it's got a bunch of videos from my upcoming MOOC. First, 2.5 hours or so. There'll be more coming soon, hopefully. And so that'll give you a good flavor of the kind of things we'll be covering in 282 in the fall. So you can watch some of that stuff. Some people say, I just got an email today saying, I like the class lectures you do better when you're not trying to read a teleprompter. That's probably true, probably more interesting. But I'll tell you what, trying to do very, very, very complicated technical material without a teleprompter is extremely hard, which is why politicians get addicted to this kind of stuff. It's hard to say things coherently. So take a look at this stuff. If you're interested in taking the course, I think, knock on wood, we've got it set up now so people don't need to have 281 as a prerequisite. You should just be able to enroll. Has anybody been able to confirm that? All right, good. So you should just go for it at this point if you want to take the class. And let's see. I guess with that, let me show you a couple other things. A couple people had some common problems in class today, and so I thought I would take a minute, or in office hours today, take a minute and talk about a couple things. So if you compile your code and you get like this really weird error and it doesn't seem to understand the types you're trying to use for Q, you're probably forgetting to include array.h and q.h somewhere. And there are various places you could put it. You can put it in q.h, you can put it where you need it, etc. But just that's probably what's going on. So you get insane compile errors. That's probably part of the problem. Another problem is that for assignment 4C, which is the one that's due now, we don't use the composite pattern for the nodes. It's a very simple node hierarchy. So you can do a few things in your implementation of the except method in tree that are not strictly correct, and it'll still work. But remember that tree is playing the role of the abstraction class in the bridge pattern. And as such, what it should be doing is it should be saying root underscore, because root is the pointer that plays the role of the bridge to bridge from the abstraction to the implementer hierarchy. It should be saying root underscore and then calling the method that was called on the interface class. So if you call the method right on the interface class, it should delegate to the root arrow right method. If you call left on the interface class, it should delegate to the left method through the root pointer. If you call except on the interface class, it should delegate to the except method on the implementer hierarchy and so on. So if you are getting weird compile errors there, it's probably because you're not properly forwarding the calls. So just be prepared for that, and don't be surprised if you run into that problem. Anybody else having any other weird problems? If you're having other weird problems, again, come to office hours and we'll sort them out. Lawrence?
Could you explain a little bit more why you can use feed.visit star this in the node, but you can't do it in the tree?
Because the tree class doesn't know anything about the hierarchy of composites. Now keep in mind, we're talking about assignment 4D here, right? Not 4C. 4C doesn't use composites, but 4D does use composites. The tree class has no earthly idea. It doesn't have any subclasses, right? It's just an abstraction. So the node, component node, which is what ref counter will hold and forward to, that guy actually has a hierarchy of nodes. So you can't, if you call visit on the tree, it's a visit. What are you talking about, visit? I can't visit anything here because it's not the right type. But if you visit on the node, then the node has all the methods that it can use for the double dispatching. So it has leaf node and composite add node and composite unary node and all those kinds of things. Patrick?
How are comments and the like going to work for 4D? It's due, the day after the last day of class for us?
So you should turn it in and we'll get it back to you, and then you have two choices. You can either let your grade be the grade that is the submitted version, or if you want to, you can have the grade be the version that we give you comments back on and then you address before the end of school, right, before grades are due. So, and not like the night before grades are due, but a few days before grades are due, because we have to actually grade them. Other questions? All right, so let's do a couple things. Let's do the quiz. So what the heck does all this code do? So basically what this was asking was, do you understand how virtual functions work? And hopefully the answer is yes. So when you compile this code, it doesn't work. Why doesn't it work?
Because you try to call a virtual method, your virtual method, in the base class.
Calling it, well, it's actually a little bit more fundamental than that. Yeah.
There's no pointer where BP arrow foo because it equals 0. Because it's not like a function.
Where?
The first BP foo.
Oh, up there?
In main, when you do BP arrow foo.
No, I think that's okay. Well, yeah, that's fine. It's a more fundamental. It's a compile time problem.
Bar is not a virtual function. Virtual method.
That's okay. That's okay.
You're compiling, or you're calling a method that doesn't have implementation.
That's not a compile time error. there's a compile time error. Rebecca. Exactly. You can't define an instance of B here because B is an abstract class, right? It has a pure virtual method, so you can't instantiate it. All the other problems you guys were pointing out are also derivations of this, but they're not compile time errors. They would be runtime errors if you could somehow get the code to compile, which you couldn't. So that's the problem. You can't do that. OK. And how do you fix it? Well, obviously, the fix is not to try to declare an instance of B. Or, if you were so inclined, you could always make foo be non-virtual, right? So that's another way to solve the problem. Sorry, not non-virtual. You could make it non-pure virtual and provide it with an implementation. That would also work, too. All right, what methods get called? So let's assume that we fix the problem so that this code will compile. So here we have BP foo, where BP is this guy right here. So which foo is going to get called in that case? So base is foo, right? Let's see if we can keep it all on the same screen. And in this case, BP arrow bar, which method gets called? Base, right? All right, so now we call DP arrow foo. What method gets called there? So it's the derived one. And now we call DP arrow bar. What gets called there? Base. That was the trick question, right? Why is it base?
It's not virtual.
It's not virtual. So remember that only virtual methods are dispatched based on the runtime type information. If they're not virtual, then it's based on the static type. And then down here, we assign BP to DP. And now we're calling BP arrow foo, but it's actually pointing to a DP. So which will that call? Derived. And now we're calling this one. Which one will be called here? Again, it's base, right? So if it's a non-virtual method, then it's always resolved by the type of the pointer, not the type of the object. And what the heck happens when you call this stuff? Remember we talked about how the compiler keeps, in objects that have virtual methods, the compiler generates code that has a special v pointer that points to a virtual table. V stands for virtual. V pointer points to a V table. Virtual pointer points to a virtual table. And the virtual table keeps track of pointers to functions for all the methods defined in that class, that subclass or base class, that are virtual. And so when you invoke something that's a pure virtual or a virtual method, then the compiler generates code that follows the V pointer to the V table and then indexes into that V table at the slot ID corresponding to the method starting from 0 or 1 or whatever. And then it indexes into that, finds the pointer to function, and calls it, passing in the this pointer and any parameters. Yeah?
Does C++ have something analogous to super, where you can call something from your super class?
They don't have a keyword called super, but you can easily just go ahead and call up. You can keep track of your base of your parent class and just call it directly, and that'll call the parent's classes thing. So if I have a class called base and a class called derived, if I'm in derived, I can say base : foo, and that'll call the base class's foo.
And it doesn't need to be a static method or anything like that?
No.
Okay.
Sorry, you said if you have a non-virtual method and in the derived class, if you have a method with the same name, there's no like function overloading?
There is function overloading, but the message you will get is probably something about shadowing. It'll say something like the subclass is shadowing the base class method. So those methods are in fact overloaded, but they're not overridden. And so it doesn't do dynamic binding. It just will have the same name. Yeah. OK. Let's see. Next question. What's the intent of the iterator pattern? Obviously, the intent of the iterator pattern is to be able to access every element in a container, aggregate, collection, whatever you want to call it, without exposing the representation. What are the styles? You know, C++ or the gang of four style versus the STL style. What are the pros and cons of each? So the STL style, remember, what's the big thing about STL that's good? It's easier to use because you don't have to worry about memory management. But what's the downside? It's harder to implement. And then the other, the gang of four thing is just the opposite, right? So it's easier to implement, but it's a little harder to use. I give examples where iterator pattern can be applied. There's a gazillion of them. STL being one great example, of course. And Java has stuff. Java has a couple different ways of doing it and so on. What are negative and positive consequences of applying this pattern? So the good part is that you can decouple the objects or the containers from what you do to get access to their elements without exposing those elements. So it's really about abstraction. It's about flexibility. That's the good stuff. The downside is that there can be a fair amount of overhead to access every element one at a time. And so that's why there are variants of this pattern compounds like batch iterator and so on, that allow you to be able to grab a chunk of things and then iterate over them locally as opposed to having to go through a concurrency or distribution boundary to get access to them. And then the grad students had questions about the visitor pattern. And we will go back over here. Oops. Look at visitor. If I can make the screen big enough to read. Yeah, much better. Let's see. There we go. That looks like good old visitor right there. So if you recall, visitor centralized operations on an object, so you can vary the operations while still having them behave polymorphically. So that's kind of the idea. You can add operations to, you can extensively add operations to a composite-like data structure without requiring changes to the data structure itself or the methods it exposes. That's basically the purpose of it. And we talked about static polymorphism. Remember that whole wacky thing we discussed? Let's see, where was that? There we go. Static polymorphism, where some things were dynamically bound, like the accept method is dynamically bound, the visit method is dynamically bound, but which visit method gets called depends on the type of the subclass of node or component node or whatnot that's statically bound. That type is known in a different way, statically. And there's stuff about what are pros and cons of all this stuff. So the good part is you can add a lot of things. You can add new operations without changing your existing structures. The downside, of course, is if your structures change a lot, you're forever running around modifying your visitor hierarchy and your visitor interfaces and so on, and that becomes unwieldy. And then what were some examples? And there were some examples we gave, whoops, somewhere. Yeah. So mostly things that do language processing of some form or another do visitor. Language processors which have complex structures that use composite-like data types in order to do their job. OK, so that's the quiz. Let us now see. Anybody have any questions about the command pattern? By the way, I was playing around. I was doing some preparation for the videos I'm creating. And I was thinking carefully about some stuff in Android, and it's kind of cool. This is actually really a Java thing, but Android takes it sort of to the next level. So anybody here familiar with the Java runnable interface? What a runnable is? So what's a runnable?
It's basically a class that derives from runnable that you give to a thread instance so you can run that specific method.
So basically, a runnable is an interface that defines one method and one method alone, and it's called run. And you implement that interface, and you define a command that can be run. And so there's a variety of cool things. Java has a whole pile of cool things you can do with runnables, but Android really takes it to the next level, and they have this whole handlers, messages, and runnables, or hammer framework, the hammer framework, handlers, messages, and runnables. And basically what you can do, if you have a background thread in Android, you can spawn a thread and do some long-running operation, like downloading a file or something like that across a network, which could block. And when you're done, you can basically create a runnable. There's all kinds of cool magic you can do with Java to make sort of anonymous objects appear out of thin air. And you can make this thing, and you can define its run method. And then you can go ahead and post this. And the post takes the runnable that you created, which is a command, basically, and it sticks it on a queue that's managed by something called a looper and by the handler. And then the looper runs in something called the user interface thread, or the UI thread, and it pulls messages off the queue one at a time. And in the case of runnables, it dispatches their run hook method to run the command. So that's a great example of the command pattern, which is actually an example of something called the command processor pattern, which is a related pattern in the Pattern-Oriented Software Architecture Volume 1 book. But just a really nice example of kind of combining some of the things we've been talking about and putting them in a different context, like Java concurrent programming in Android. So it's neat. You often, once you understand what these patterns are, you start to see them showing up in some of the most interesting places that maybe you wouldn't have expected until you had a better sense of what the patterns are. OK, so with that, let's now go ahead and talk about, or continue to talk about, the creational patterns. So far we've talked about a couple of creational patterns. We've talked about Builder. If you recall, Builder we talked about a couple weeks ago. And that was used to make a composite object or a complex object a piece at a time. And we used that for our interpreter, in conjunction with our interpreter, for our expression tree builder. And then last time we talked about factory method. If you recall, factory method basically defines an interface for creating a product, but defers to subclasses what actual product is created. We talked about that. And then I talked about the fact that in some cases there may actually be multiple things that have to be created consistently. And so we're going to look at some examples here. And first I'll tell you what the Gang of Four book uses as an example, because in some ways it's a little bit more motivating than the example we're going to use here. The Gang of Four book talks about a windowing system. Now, way back in the day, back when the Gang of Four wrote their books, a lot of them got their experience developing user interface frameworks. So Eric Gamma, who's one of the authors, wrote a framework called ET++ when he was a grad student at University of Zurich in Switzerland. Some of the other guys did other things. John Vlasides, the late John Vlasides, had written some frameworks. He wrote something called the Interviews framework, which was another C++ framework that did user interface stuff. And back in those days, the choices that you had for runtime platforms were quite different from the ones we have today. Some things were the same, many things were different. So if you were developing user interface frameworks back in the late 80s, early 90s, when these guys were doing their work, you would had 4 or 5 different versions of Unix and different user interface toolkits like Sun Tools, or different variants of X Windows, or the common desktop environment. These are sort of older, more legacy kinds of things. And then there was a little bit of Windows kind of popping up around that time, maybe some Mac stuff, although Macintosh was considered to be sort of a different space than Unix or other kinds of platforms. But the point was that people in those days were often trying to develop platform-independent user interface environments. So the idea was you could write your code one time, and then your code would compile and run on these platforms because they would use a framework to abstract away from the differences of the underlying runtime platform, runtime environment, runtime operating system. We still do that a little bit. Some versions of Linux have a couple different choices as far as user interfaces that you might use. There's GNOME and some other stuff. But for the most part, people typically have now kind of consolidated to using the platform vendor of choice's interface. So if you're running on Windows, you're probably using Windows interface. If you're running on something like the Mac, you're using the Mac interface. But even there are often choices. So if you play around with Windows these days, you probably know you can switch themes. I don't know whether Windows 7 or Windows 8 allows you to do what you used to be able to do. You used to be able to go in and change looks entirely. So if you were using Windows XP, you could actually go in there and say, I want to make this thing look like Windows 2000. And all of a sudden, it was like time travel. You'd go back 6 or 7 years, and the world looked different. I'm not sure if they can still do that, but you can change stuff like borders and colors and other kinds of things. Anyway, the point of this stuff is, back in the day when people were trying to build these user interface frameworks, there was a motivation to be able to create a bunch of widgets. Does anybody know what a widget is in the context of user interface environments? It's kind of an ex-Windows term, but it still has meaning. So a widget is some kind of control, like a button, a radio dial, a menu, a window, a border, a scroll bar. These are all the things that you can do to overlay stuff onto your user interface to give it a different look and feel. Now again, nowadays we kind of accept whatever look and feel we're handed, but back in the day you used to be able to tweak these things. So one of the things people wanted to be able to do is they wanted to be able to come up with ways of emulating a consistent look and feel for a particular theme for user interfaces. So for example, if you're going to be writing the Windows 2000 view or theme or whatever you want to call it for Windows XP, you want to make sure that when you're in that mode, everything you do, every window you create, every button you create, every radio dial you create, every slider, etc., has the Windows 2000 look and feel versus, say, the Windows 7 look and feel versus the Windows XP look and feel, which are all slightly different, right? So the theme here is whenever you go to create a widget, whatever they may be, you want to make sure that the widgets you create are all consistent based on the theme or the mode that you're in at that point in time. So think about that. You've got a bunch of things you have to create, and you want to make sure that they're created in consistent ways, semantically consistent ways. And that's what motivates this pattern. The pattern is the abstract factory pattern. And an abstract factory is basically just a collection of factory methods that do semantically consistent creation for a group of related products. Right? So going back to the user interface example, we have a bunch of things we have to create. Windows, scroll bars, borders, radio dials, et cetera, et cetera. And when someone's in the Windows 2000 theme, every time they say, make scroll bar, make border, make window, we want to get back something that's consistent for that theme that we're currently in, the mode that we're in. And so the abstract factory pattern gives you the tools to do that because it allows you to co-evolve a group of factory methods as a whole, as a unit, and therefore you can make it easier to ensure semantic consistency. Any questions about that? So in our particular case, well, we'll talk more about how we're going to use this, but basically that's the abstract factory pattern. You want to be able to create factories of related objects without specifying the names of the subclasses. Same basic reason why you use factory method in the first place, right? You focus on product, which is the abstract thing, and you leave it up to the factory implementation to decide what kind of concrete product to make. And all we're doing here is we're just taking it to the next level. So as you can see in this particular example, you've got an abstract factory, which has a bunch of factory methods defined in it. And each of these factory methods creates an abstract product, the corresponding abstract product. So create product A creates abstract product A. Create product B creates abstract product B, and so on. And then you subclass abstract factory, and you fill in the methods to create the appropriate concrete instances of these guys. But naturally, they are returned as abstract instances, much like we showed with the factory method pattern. But now we've got a group of them that all manage to be used together. So we're going to use this basically to create different kinds of things. So we might want to create groups of a bunch of things having to do with commands, a bunch of things having to do with iterators, a bunch of things having to do with visitors, and so on. We can co-evolve those and then make it a centralized factories role to create all these different kinds of entities in various kinds of ways. By the way, we had an interesting discussion at office hours today about the difference between command and factory method. And if I hadn't already had created the quiz, I would have made that a quiz question. It's a good question. So does anybody want to guess or take a shot at what the difference is between factory method and command? How do they relate to each other?
Well, both kind of make an interface between the implementation subclasses, generally speaking.
Yep.
But
As do almost all the Gang of 4 patterns, right? So that, I mean, your observation is very good. But I think where you're headed was that doesn't really differentiate them, right? That property. Anybody else want to take a shot at some things that can be used to differentiate these different design abstractions? Rebecca.
Command is more of a behavioral pattern, so it deals with creating individual commands that can be utilized for all different objects that you're calling it, whereas factory is more creational, so it lets the subclasses decide which one to instantiate.
Great. So that's a really good distinction right off the bat. All the factory, the factory method, abstract factory, singleton, prototype, and so on, those are all creational patterns. They make stuff. And stuff like command and strategy, those are structural behavioral. So in some sense, they are the targets of what the factories make. So kind of as we talked about in office hours, you could use factories, factory method, abstract factory builder, and so on, to make commands, different kinds of commands, to make iterators, different kind of iterators, to make visitors, different kind of visitors. So the concept of a factory is a very generic concept. Now what the factory makes starts to get us into more specific kinds of things. So in the case of a factory that makes a command, then you get something back that's going to have a method called execute or run or whatever. And then you can queue it and undo it and redo it and all the kinds of things you do with a command. If a factory makes an iterator, you won't do command-like things to it, but you'll do iterator-like things to it. If a factory makes a visitor, you'll do visitor-like things to what it makes. So the concept of creation is very fundamental. And what it creates itself could play a different role in the hierarchy of the design you're trying to do. So those are just some other kind of ways of differentiating those things. It's very interesting to think about how the patterns compare and contrast. And the way you really learn about this in practice is by seeing how they work. You actually implement them, and then you can say, what makes sense? Should I use this here? Should I use this here? By the way, I should just to point out, if you ever have a chance to watch the Safari videos I did on design patterns in Java, with some help from John last summer, we basically created a really cool implementation that had, I think the way it worked was we used a command. Let's see, how did this work? It was factory and command were used together. I think the way it worked was that you would make a factory that would create commands, but itself was implemented as a command. So the factory itself was implemented as a command. There's all kinds of crazy things we did with kind of combining the patterns. And there's certain things that you also do a lot in Java just because of the way it deals with anonymous types. And if you take the 282 class, you'll get a great first-hand experience with programming all these anonymous types. And it's really cool. The anonymous programming patterns and idioms in Java are very cool in much the same kind of way that the generic programming mechanisms in C++ are very cool. And they're actually very cool in much the same way, but they differ in that the stuff in Java is more about dynamic binding, whereas the stuff in C++ and STL is more about static binding. And does anybody want to hazard a guess as to why C++ best practice emphasizes static binding versus Java, which emphasizes dynamic binding? Go ahead. Java has garbage cleanup. That's good. Other guess? Okay. Lawrence, did you?
That was mine.
Okay. So that's certainly one thing. You don't have to worry as much about ownership with dynamically garbage collected languages. But there's something else more fundamental about that, the reason why C++ emphasizes static stuff. John?
Well, I guess Java's meant to be more portable, and so there's a bigger emphasis on working across systems where dynamic binding will be going on.
Okay, I think portability is a little orthogonal to this issue, but it's an interesting observation. Anybody else want to take a guess? Why do people use languages like C and C++? What's the driving factor typically? Efficiency, right. So as a general rule of thumb, static bound stuff will be more efficient, typically, given some generation of technology. It'll be more efficient. And why is it good? Why are statically managed things more efficient than dynamically managed things as a rule?
More of the work is done at compile time.
More of the work is done at compile time, more information is available to the compiler, some commitments, some optimization, some global analysis can be done, so you can really optimize the heck out of the code because you have full information at that point. When it's statically bound, statically compiled, statically managed, you know everything there is to know, more or less, about the way it's being used. Whereas dynamically, you could figure it out, but it would take you so long to figure it out often that by the time you figured out the best way to do it, you might as well have just run it in the first place, right? Because it wouldn't be, the optimization, the time spent doing optimization wouldn't be worth the overhead of taking the time to do the optimization. I'm sure you've had this kind of experience before where you have friends who want to super optimize the planning for something, and by the time they super optimize it, you could have gone out and done it and come back 3 or 4 times, right? So that's kind of the issue. So C++ and C, but especially C++ in this case, is typically used for more performance critical tasks, and so people are willing to give up some flexibility to make the result run faster. Whereas with Java, it's almost always the other way around. People usually use it for stuff where human productivity is the key factor, getting it done quickly, getting it done right. Maybe it runs a little slower, but that's okay because it's not doing something that's time critical, or it doesn't have to scale up to n million entities or something like that. So there are different design points, different purposes for trying to do different kinds of things. All right, so let's take a look at an implementation of some of this stuff. So here's an abstract factory implementation. This is kind of a fun thing. So here's my implementation of the command factory. And this, again, of course, uses the gang of 4 model of the pattern. And then we throw a bridge around it to deal with memory management with C++. So if you take a look, we've got a map called the command map. And all the different kinds of commands that we have, like print, eval, format, expr, those are all added as entries in the map. And it's probably no big surprise that that this map is an STL map, just a good old map. And it maps strings, but what it maps is kind of cool. What this map maps are strings to pointers to functions. And actually, not just pointers to functions, pointers to member functions. So for every element in here, we stick a pointer to a member function in under its name. And then here's the actual lookup operation for how we're going to do this thing. So what we do is we come in the make command. Make command is one of the factory methods, right? It's the primary factory method. But it uses a bunch of these other factory methods that are part of the abstract factory, right? So it has print, eval, expr. Those are all things that it's actually doing based on whatever you pass it as a command. And so what it does is it comes in, and you can see it goes ahead and looks up the name of the command that you gave it. So you give it an input string. It pulls off the command portion, the front part, like print. And it goes up and it looks in the map. And it gets back an iterator to whatever it found. Now, if it didn't find anything, like if you looked up something called foobar and there's no foobar command, well, obviously it's not going to do anything in that case. But if you look up something and you get back a real command, what it does is it takes what you gave it, because remember iterators for maps have 2 parts, a first and a second. And it goes ahead and it grabs out the second, which is the pointer to member function, and it goes ahead and invokes the pointer to member function, passing in the parameter that you passed, or the parameters you passed to the command. So what's cool about this is you can do these really super duper optimized lookups that are all entirely table/map driven, thereby completely getting rid of the need for a bunch of if-else statements. We don't have to say, if the command equals print, then call the print method. Else, if the command equals eval, call the eval method, right? Those things are all subsumed into this really cool use of map, which maps strings to pointers to member functions. Any questions about that?
It seems like the obvious benefit of that is that it makes your code a lot cleaner. Is there, I guess, a lot of extra overhead for doing that?
Yeah, great question. So let's break it down. So clearly, arguably, because somebody would argue this, this code is arguably cleaner and easier to understand once you have a deep appreciation for what's going on, right? And the reason it's easy to understand and well, it's easy to maintain is because you have one place you add your commands and the implementations of said commands. You put it in a constructor or some initialization method or whatnot. And then when you want to go ahead and do something, you just look it up in the map and you get it back and you run it, right? So there's no complicated if statements that have to be maintained. So from that point of view, it's very concise. And then the question becomes, the two questions that are important are, is it easy to understand logically, and does it run efficiently? Okay, so let's look at those one at a time. If you didn't know about this particular little idiom, you might not think this was clear, right? If somebody was used to looking at traditional code and they didn't understand that particular idiom with maps and pointers to member functions and strings, they might be befuddled for a little while. But it's not a hard thing to learn. So once you understand it, you're like, okay, I get it. It's the table-driven function invocation idiom, or whatever you want to call this thing. So I think it's arguably easy to learn, and it scales up very nicely, especially as you have a large number of commands. From an efficiency point of view, it really depends on what the alternative is, right? So certainly from an asymptotic time complexity point of view, find is what? Log n, right? Because it's a map. It's a red-black tree under the hood. So comparing, if you have a large number of commands or large number of operations, looking something up in a map will take log n time, compared with if command name equals foo, then bar. Else if command name equals baz, then foobar, right? What does that turn into? That's linear search, right? So asymptotically, this will scale better. And then the only other real question is there any appreciable overhead of using this stuff? And the answer really is no. I mean, you're basically just looking things up, and you're getting it back, and you're just calling things through a second pointer in a pair. The other nice thing is this code is more concise, so you may get better locality of reference as well, because it's going to take up less space. The locality of reference and cache affinity is a determining factor in systems when you're constrained on physical memory.
Would you be able to, would it be feasible to put lambda expressions when you're making your map?
Oh yeah, sure. Yep. Yeah, isn't that cool? So you could stick lambda expressions in there, and then that's actually very much like what Java does, right? Java's anonymous inner classes are very much like lambda expressions in a lot of ways, because they're not really named, but you can hold on to them and do stuff with them. Yeah, because remember, lambda expressions can be used to create anonymous functors, and you can just pass those things in as functors, and then you can just call them like you normally would. So that's pretty cool. All right, so pros and cons of Abstract Factory. Very flexible. If you do it right, your application code has no dependencies whatsoever on names of subclasses. The lexical dependencies have been almost entirely removed. Very abstract, and you can do some cool semantic checking. One of the nice things you can do with Abstract Factory is you can ensure, through some human awareness and human effort, that the subclasses create things that make sense in a semantically consistent way. Going back to the example we talked about before with the user interface framework and theme, the subclass implementer of whatever Windows system you're trying to emulate, be it Windows 2000 or Windows XP, whatever theme you want, they can make sure that everything in the subclass creates the appropriate type of widget relative to that kind of theme in that particular subclass of the Abstract Factory. So you just have to make sure that you're doing them all in some kind of consistent way. Any questions about that? So that's what semantic consistency means. The downside is, as with almost all these patterns, especially the ones like Composite, Abstract Factory, and Visitor, you got these hierarchies, and they have a lot of methods. And if you start making changes, you have a lot of things to change. And so it becomes tedious to work with. But this is the classic thing, right? Easy to use, hard to implement. Now, in the grand scheme of things, what would be the circumstances under which you would care about ease of use versus ease of creation? What would be some reasons why you would choose one approach versus the other?
Well, if you're Microsoft making a Windows interface, you want people to develop for you, so hopefully make it easier to use.
Great. So if you're a platform provider, so Microsoft, Apple, Google, so on, you ideally want to make it easier for people to write apps using your APIs, because if you do, they'll be able to create apps, and then you'll get an ecosystem that's more thriving and more enriched. In fact, that's actually one of the knocks at the moment against Microsoft, is they've struggled to keep up with that. They actually stumbled for a long time for a variety of different reasons. And I think they've gotten a lot smarter over the last few years. But for a long time, their platforms were sort of unnecessarily hard to work with relative to other things. A great example of this would be Nokia and their Symbian platform. I don't know if anybody here remembers Symbian. Symbian is kind of an old school platform that was actually really cool in the day. Back in the early days of mobile devices, Symbian was like the user interface environment and framework of frameworks for doing mobile application development. And it was way, way, way better than the competition. But unfortunately, it was done in kind of an old school way, using older commitments to languages like C++ that really weren't thought out very well with modern software techniques. And so as a result, it was next to impossible to add newer features to Symbian-based devices, like touchscreens was really hard because of the way they'd architected the system. And it was also just hard to write Symbian code. I don't know if you ever looked at how to write Symbian code, but it was very hard. It was not for the faint of heart. They used a lot of really cool patterns, but it was very crufty. And then along came Google with Android, along came Apple with Objective-C, which is arguably still crufty and weird, but we'll leave that aside. But let's focus on Android. So Java's way easier to program than C++ in the way it was done in Symbian. And so within a very short time, they'd completely leapfrogged the type of things you could do with Symbian. And as a result, nobody wanted to write Symbian apps anymore. And then it became a self-fulfilling prophecy, much the same kind of problem that RIM/BlackBerry has run into. You start falling behind in the ecosystem wars, and people don't want to write for your stuff because there isn't as much cool stuff for your stuff, and so it becomes this sort of convoluted death spiral kind of thing. So that's just a good example of how not understanding the trends in which technology is moving makes it difficult to be able to keep up. So a lot of the stuff we're talking about here has very specific meaning and purpose, and that's why it's so cool when you look at Android. The whole thing is so patterns oriented from top to bottom. And as I'm going through this stuff, making the slides, it just never fails to amaze me how many cool patterns that we cover here are also found in Android, plus lots and lots of other ones that we haven't had a chance to cover here. All right, so there's a bunch of different issues. How do you parameterize the interface? Do you just have lots of methods? Do you have templates? Do you have other factories, nesting of factories? How do you determine who creates the factory? So if you have you have some kind of thing where you're going to be able to shift between different user interface themes, who figures out which themes to do? How is that done? And sometimes you can use the prototype pattern to make that easy to do, especially if you want to be able to change these things on the fly. And then the other insight, which I think is so funny because it's so obvious if you've looked at this stuff for a while, but it doesn't really appear in the Gang of Four book, abstract factories are essentially groups of factory methods. There really isn't much more to it than that. They're very much related to each other. And there are lots and lots of known uses, lots of Windows systems, and lots of middleware, and so on and so forth. Okay, so to wrap this part up, we saw how three patterns are used together here. Abstract factory is a pattern that can be used to create groups of semantically coherent factory methods. Factory methods can be used to create various kinds of products, such as commands. They can also create iterators and visitors and so on and so forth. So for this particular part of our design, these patterns work together. And you see factories used with all the other patterns we've talked about for the most part. You can use factories to make iterators. You can use factories to make visitors. You can use factories to make commands. You can use generalizations of factories like builders to make composites. Right? So there's a lot of relationship between these patterns. They're very strongly connected, and you typically use them in groups. So you don't use them in isolation. Okay. And so this basically allows us to add new operations in a flexible way. All right, so what we're going to cover next time, starting on Monday, will be the state pattern. And we should probably get through that pattern in one day. It's one of the more complicated patterns in the Gang of Four book to explain, at least in the way that we're trying to do it. And after that, then we're doing really well. So let's see, Monday is going to be the 14th. And that means we'll have just a couple more classes after that. So I think we're doing really well. We should get done with all the material in these slides by the time we're done with the end of the class. All right, so without further ado, let's do the quiz.